Hello and welcome to yet another Combinatorics video of Cornerstones of Math. Without further ado, let us dive right into the problem. 9 identical transparent cubes are arranged in 3x3 configuration as shown on the bottom left. Here, some transparent cubes are replaced with opaque cubes of the same size so that the front view and the side view of the cubes look like the bottom right part of the figure. So the front view looks like this, and the side view looks like this. Now, many of you may easily answer the minimum and maximum number of cubes that must be replaced. The minimum case is replacing 3 cubes, like this top view for example. And of course, the maximum case is simply replacing all 9 transparent cubes into opaque ones. But we are not interested in these cases. Instead, we are going to answer the following 2 problems. Problem A is find the number of different arrangement of cubes when 5 transparent cubes are being replaced with opaque ones. And problem B is find the number of different arrangements when 6 transparent cubes are being replaced. One more rule here. In this problem, we do not consider the duplication by rotating or flipping the entire arrangement of cubes. That is, each row and column is considered distinct from one another. For example, in the case of replacing 3 cubes, these 2 cases are considered different, even though we can rotate one arrangement to obtain the other. So with problems and rules settled, let us solve the problem. Problem A, replacing 5 transparent cubes. We are going to use the approach where we ask the question, how many cubes have to be replaced in each row? Well, one thing we know for sure is that if there is a row where none of the transparent cubes are replaced, then we have an invalid side view. That is, at least 1 cube from each row must be replaced. With this in mind, if you examine some valid examples, you'll notice that we can divide them into 2 cases. In the first example, in one row, all 3 cubes are replaced, and in other 2 rows, only 1 out of 3 cube is replaced. In the second example, now there are 2 rows where 2 cubes are replaced, and in the remaining 1 row, only 1 cube is replaced. These are 2 possible cases of expressing 5 as the sum of 3 natural numbers, and these will be our case 1 and case 2. The first case is when one row contains 3 opaque cubes and other 2 rows contain 1 opaque cube each. That is, 3-1-1 arrangement. There are more than just one way to count the number of cases, but here I will show you just one way. So we have these 3 rows with these many transparent cubes need to be replaced. First, we must choose which row will be the row where all 3 cubes are to be replaced. And there are 3 different rows. If you want fancier expression, you can consider this as 3 choose 1, choosing 1 row out of 3 different rows. Next, for the remaining 2 rows, we replace 1 cube from each row. And you can easily notice that within each row, you can choose any position out of 3. Whatever cube you choose to replace, it will generate the valid front view and side view. Therefore, there are 3 ways each to select a position for the opaque cube, or 3 choose 1 ways, choosing 1 position or column out of 3. Therefore, the number of cases is 3 times 3 times 3, which gives 27. The second case is when 2 rows contain 2 opaque cubes each, and remaining 1 row contains 1 opaque cube. That is, now the 2-to-1 arrangement. As for this case, we need to divide cases further into 2 subcategories. The first case is where 2 rows containing 2 opaque cubes are identical, and the second case is where 2 rows containing 2 opaque cubes are not identical. The method of counting differs between those subcases. First, when 2 rows containing 2 opaque cubes are identical, then the remaining row has only 1 possible location for an opaque cube. That is, its column index is automatically fixed. Here, we first choose positions for two identical rows where two cubes are to be replaced. There are 3 choose 2 ways. Then, within these 2 rows, we choose 2 column positions to determine the cubes to be replaced. There are also 3 choose 2 ways for each row. As I said, the last row is fixed, hence the total number of cases is 3 choose 2 times 3 choose 2, hence 9. Next, when 2 rows containing 2 opaque cubes are not identical, then we must think about how many different rows are there when 2 transparent cubes are replaced with opaque ones. There are these 3, which I will call A, B, and C. We know that there are 3 ways because there must be 3 choose 2 ways in total. Then we select 2 different rows from arrangements A, B, and C, which will become these 2 rows that are different. There are 3 choose 2 ways to do so. This determines these 2 rows, but what about the remaining row with 1 opaque cube? Well, you can realize that in this case, the remaining opaque cube can go wherever within the remaining row. This gives the possible number of its position 3, or 3 choose 1. Finally, we have to arrange these rows in a grid, and since we have 3 different rows, there are 3 factorial ways to arrange them. This gives the final number 54. Therefore, adding up all the numbers from all cases, we obtain our final answer, 90 ways. So this is the answer for replacing 5 cubes. And if you understood the previous problem, then problem B is easy. Now we replace 6 cubes. Therefore, we investigate how many ways are there to express 6 as the sum of 3 natural numbers. We also have the condition that none of these natural numbers exceed 3, and you can easily find out that there are 2 ways, 3 plus 2 plus 1, and 2 plus 2 plus 2. So we have 2 cases, 3 to 1 case, and 2 to 2 case. As for 3 to 1 case, we simply find the number of ways to replace cubes within each row. As for the row where we replace 3, there's only 1 way, or 3 choose 3 way. As for the row where we replace 2, there are 3 choose 2 ways. And as for the row where we replace only 1, there are 3 choose 1 ways. Notice that there are no such forbidden positions, because one row having all 3 cubes replaced automatically guarantees the valid front view. And then we arrange these 3 different rows, hence 3 factorial. So if we multiply all of these, we obtain 54. As for 2 to 2 case, then we bring back these 3 arrangements A, B, and C where 2 cubes in a row are replaced. Now, each row in a grid chooses from A, B, and C, and this gives 3 choose 2 cubed ways. However, there are invalid cases included here. More specifically, AAA, BBB, and CCC combinations are invalid since they give invalid front view. Therefore, we must exclude these 3 cases, which gives 24 ways. Therefore, from cases 1 and 2, the total number of ways is 78 ways. And that's all for today's video. Thank you all for watching. Please don't forget to give a like if you enjoyed this video, and I will see you in another video.